Raoult's law states that the vapor pressure of a component is proportional to its mole fraction. So if you increase the mole fraction, you increase the vapor pressure. This is Raoult's law for solutions. Now, for gas solubility, we use Henry's law. It states that pressure equals the constant times concentration. Henry's law states that gas solubility is proportional to pressure. This soda bottle here is a perfect example. High pressure forces the CO2 to dissolve. Colligative properties depend on the number of particles, like in melting point depression. For instance, salt water's melting point is lower than pure water's. So for NaCl, it breaks into two ions, giving us an I value of 2. But glucose doesn't dissociate, so its I value remains 1. So when we add a non-volatile solute like salt to water, the vapor pressure of the solution decreases. This is the lowering of vapor pressure. The elevation of boiling point. This is because adding a solute lowers the vapor pressure as shown in the diagram. Solute particles disturb solid formation, so freezing point decreases. This is why salt lowers the freezing point. First, vapor pressure decreases as per Raoult's law. Boiling point rises and freezing point drops, and osmotic pressure increases. In reverse osmosis, water is forced through a membrane. Contaminants are behind producing pure water. This is driven by applied pressure. In reverse osmosis, we apply pressure to condense water molecules through the membrane to the pure side. Solute molecules are left behind. Okay, let's start with step 1. We calculate the moles of benzene and toluene. For benzene, it's 80/78, giving us 1.026 moles. In step 2, we find the mole fractions using the moles from step 1. Then in step 3, we apply Raoult's law to get the partial pressure. In step 4, we use Raoult's law. The mole fraction of benzene in the vapor is its partial pressure over the total pressure.